All right. Hello, everyone. I'm hoping to discuss my research on modeling emergent dynamic metabolic interactions within microbial communities. This has been part of my research for the last year, and so culminating hopefully in a publication soon. Overall, we're interested in bacterial metabolism because it's a vast network that influences our day-to-day life. You look at all the microbes and their reactions at the center here and how they interact with all the interactions in our human body. We can see that there's a lot of vast interactions total. And my lab specifically focuses on butyrate, which helps to reduce inflammation in the body, but isn't made by the body. It's made by different bacteria, and so understanding what bacteria produce it or consume it could be really pertinent to uh, other health facets. And so the way that we understand and model microbes is through genome scale metabolic modeling, which allows us to map genes to reactions and then run flux balance analysis on that. This allows us to represent the flow of nutrients through a microbe and its metabolism, and understanding the outputs that come out. This allows us to individually model an individual microbe where we maximize total biomass, and then we give it constraints such as steady state for ensuring there's not more nutrients created or taken up than is actually available, and also for um, turning on or off reaction bounds through these. This also allows us to model a media for a culture simulation. Scaling up to community scale metabolic models is a little more tricky and requires some considerations. Notably, the main one that I use most is compartmentalized modeling because it's the fastest. It does this by uh, simulating each microbe as their own compartment within a greater model and then simulating the interactions. And the way that it's so fast is that it's just a single larger linear program like before that maximizes total biomass. This isn't necessarily the best though because it uses the simplification that of that total biomass, which isn't biologically relevant. And so the way that most people model the total individual optimization is through dynamic modeling, where we take small time steps and update media as we go. This is much more biologically relevant, but it's slower. And so we were seeking to create a model that's a little bit in between these. And so this is where giFBA comes from. And with this, we have an iterative map that works that doesn't work in continuous time like DFBA. And the core driving function here is still FBA, where we maximize each microbe, but we do add an overconsumption adjustment by setting competition rates equally. This allows us to include the biological assumption that microbes have similar uptake mechanisms within them. And so being able to use GIFBA, we could then look at a network like this, where one microbe and its reactions are shown here and another here, and all of the interactions that occur with the environment and with each other in orange. This is a pretty complex hairball and would then be used from GIFBA to parse out the networks and the pathways that actually are pertinent for whatever metabolite of interest. But looking at a toy model allows us to more simply look at this. And so this is one toy model that we looked at that models the competition between microbes and cross-feeding, which are two primitive interactions that exist in real models: competition, fighting for a resource, and cross-feeding, where one benefits another. And so this network has both, with some coupling that ends up occurring very interestingly. Each microbe does optimize its own biomass, shown in bold. And then the parameters that we could use for bifurcation analysis are the stoichiometries of the network, along with the bounds or the relative abundance, or how much of each there are. And the states rely on the media that's exchanged throughout. And so we decided to run some bifurcation analysis on with the relative abundance parameterization. Here we take we run the simulation across all these parameters, and we get what I find to be a pretty beautiful bifurcation plot. I'm a little biased, but just the geometry is very nice. The interesting thing here that we find is some period doubling bifurcations, or period doubling occurring on the right side here, and then uh, some weird contraction happening at the bottom, some period 4 behavior and down. It does look like we hit some period doubling and then going back to a single point and more, and bouncing back and forth, maybe hitting period 3 here, but we never actually hit period 3 and we never hit period 1. And this is evident based on both this plot here showing that there is no period 1 within that period 2 section, or period 3 or 2 otherwise. But we also see that there's only one period doubling bifurcation that occurs, and that's indicated by this drastic jump in the number of iterations it requires to converge, which is evident, or which is a key feature of period doubling. The rest of these sort of bifurcations seem to be uh, border collision bifurcations, and this is based on the linear program, which optimizes uh, the objective function and finds different vertices of a polytope. So what's happening here is just the inherent function is bouncing between these different polytopes, and it's getting very close, but it's not hitting these. I want to look into that, zoom into that period doubling bifurcation with a little higher precision and see what happens. And ultimately, it just revealed the same behavior as before, where we jump from period 2 on the right to period 4. There is no other variables that we missed. And so we then took a step back and decided to look into different initial states, being able to see the stability and sort of understand the Lyapunov exponents that might be here. And what we see is that overall, for the 10 systems that we looked at with fairly large perturbations of about zero point 0.2 or 0.33 units of flux, we see that these systems remain very similar all throughout, regardless of that. And so the result is that um, that this system must be within a fairly stable basin of attraction. Overall, then this kind of leads me to want to research and look into other parameters like the stoichiometries and bounds that um, might lead to different dynamical behavior. But this is just one toy model. There are infinite that we could look at. Overall, this has been my research for the last year, and being able to look into this dynamical behavior was really interesting with the period doubling and border collisions. And I wouldn't have been able to do this behavior analysis without wonderful help from all these folks and Dr. Danforth, who helped at the beginning of the semester when I first kind of discovered this dynamic behavior. Yeah, thank you everyone for listening.